Hello, in this video I'm gonna try to explain the MMF distribution in an electrical machine. So first I'm gonna start with trying to show how we can get from an inductor with a core to an electrical machine, so we can know where the MMF is coming from and have a grasp. Okay, so here we have the first case. It's just a coil in a core with a infinitive permeability. So as we have seen before, when the permeability tends to infinitive, the reluctance tends to zero. So we are just taking the reluctance of the core as zero. Okay, so here we are gonna have a source due to the coil. That's gonna be Ni, and we are gonna have one reluctance due to the air gap, and we are going to call it Rg. And if we measure the voltage or MMF drop in Rg, it's just going to be Ni because it's in parallel with the source. Now we have the second case. If you notice here, the direction of the current changed. Now it's going the other way. So we have here for the second case, and now we separated the terms. Half of them are up and half of them are below, so we can show it as if we have separated the source. Half of the terms I, we have the sales reluctance Rg, and we have the other half of the terms I here. So that's how we got this. Now we have this third example, and for the third one we just added a leg. So we have the same circuit, we have our two sources and a reluctance Rg, and we just added one leg here. Now if we try to measure the MMF drop in Rg, so let's do it with this one. If we just do the KVL, we can see that we have 0 equals to Ni over 2. This is one of our sources, minus the drop in the reluctance plus another Ni over 2. So the drop in our reluctance Rg is just gonna be Ni. So the drop here energy is just Ni, and this is what we are seeing here, Ni and Ni. Now for the fourth example, we divided the reluctances, the spaces, we divided in two. So we have here one of our sources, Ni over 2. We have a reluctance that is smaller, Rg over 2. We have another reluctance that is Rg over 2. And we have our source, Ni over 2. So now if we measure the drop in just one resistor, is gonna be Ni over 2 because it's half the reluctance, and these two are equal, so we have Ni over 2 as a drop in this air gap. If we are looking just in this air gap, the drop is going to be Ni over 2 and it's going to be the same drop in both of them. Okay, so now we have our fifth example here. Alright, this is the same that the fourth that we have before. Now what we are doing is this air gap over here, we are distributing it around this space. So if you remember, reluctance is just the length path over the permeability times the cross-sectional area. So as long as we maintain this cross-sectional area the same as this one, both both reluctances are going to be the same. And since both reluctances are the same, we still have the MMF drop of Ni by 2. And now for the final case, we just closed the space that we had here, and now we are going to have one source again. It's going to be Ni. We have our two reluctances, Rg over 2 and Rg over 2, and the drop in one of this is going to be Ni over 2. So for an electrical machine, if we look at this air gap, the MMF drop is going to be Ni over 2. Okay, now that we know that our drop is Ni over 2, we can see in space, in a given moment, what is our MMF. So here we have 0 degrees. Here we have our 180. Okay, so we know that when we have our dot, we have 0 degrees, and when we have our cross, is 180. Now we are going to have as a convention that whenever the flux is going into the rotor, we are going to say that is positive. And whenever the flux is going out of the rotor, we are going to say that is negative. So if we look at this, from 0 degrees here, 0 degrees up to 180, we have positive MMF. So, and we know that MMF in over 2, so let's say that we have an I of 4, I'm sorry. So our MMF is gonna be 4, and we have 10 terms. So 10 terms, so we are gonna have 4 amps, 10 terms over 2. This is gonna be 20. So we know that from 0 all the way up to 180, we are gonna have positive flux that is gonna give us positive MMF. So up to here, and then when we go from 180 to 360, we see that the flux is going out, so we say that the MMF is negative from the rest of the side. So this is how we are going to start calculating the MMF over space in an electrical machine. Okay, now we have three coils. So first we're going to name them. We're going to name this one 1. So we're going to name, whenever there is a dot, I'm going to name it the normal number 1. And what is the cross? That is where the conductors are going into the page. I'm going to have an apostrophe. So 1, I'm gonna call this one 2. So here where the coils go out, go into the page, it's gonna be 2 dash. Here we have 3, and this is gonna be 3 dash. Okay? So we have the convention that whenever there is a cross, it means that the coil is going into the page, and whenever there is a dot, it means that the coil is going out of the page. Out of the page like this. So they are connecting behind the picture. Okay, so now we need to draw the MMF for each coil. So let's do it for the first one. So here we have the graph. So first we need the magnitude of the MMF. So we know we have 5 conductors, and each one is carrying 5 amps. And we know that in the air gap, the drop in the air gap, as we calculated before, is Ni over 2. So we divide this by 2. So this is going to give us a MMF of 12.5. So here we have 12.5 and minus 12.5. Okay, now we do the same. We know this is 30 degrees separation, so we know this is 90 degrees. So we know that we are going to have something at 90 degrees. Here we're going to have something as 270 degrees. And then we're going to have 360. So we do the same analogy. We know that the flux is going this way. So from 0 degrees to 90 degrees, the flux is going out of the rotor. So we are going to say that is negative as a convention that we just decided. And now we know that from 90 degrees to 270, the flux is going into the rotor, so the MMF is positive for this period. And then we repeat the cycle from 270 to 360. It is, I think this 360 is a little bit far away. 360. We know that is negative. Okay, now we are gonna do it for the second coil. We have the same at the beginning. We have the magnitude doesn't change. Here we have of 0. Now, if we look at this, we can see that the coil 2 is 30 degrees behind the coil 1. So this means that from 0 to 60, the flux is going out of the rotor. And in our convention, this means negative. So let's say 60 is here. This is minus. So we have minus until 60. Okay. And now, if we look at here, from 60 degrees to here, and now how can we know what degrees is this? It's easy because we know that it is 30 degrees behind coil 1. So here we had before 270, so here we are going to have 240 because it's minus 30 degrees. So minus 240. So we know that during this space, the MMF is positive in this moment of time. And now we know that the cycle repeats itself. So all this space up to here, the flux is going out. So as our convention is set, since it's going out, is negative. And we do the same for the third coil, but the third coil, instead of being behind 30 degrees from coil 1, we know that it is 30 degrees in front of coil 1, so 90 plus 30, so we are gonna have it 120 here, and we know that this space is negative. Then we have 180 degrees positive, that's gonna be until 300, and then it's just gonna repeat itself. Okay. So now to calculate the total MMF, we just need to add these three graphs. So here we are gonna have a maximum of 37.5, because when we add the three, there are gonna be spaces where we are gonna be adding the three, so we know that this is gonna be the maximum we're gonna get. We are gonna have our 12.5, our minus 12.5, and our minus 37.5. 37.5. Okay, so we just start seeing the graphs. We know that at 60 degrees we have minus in the coil 1, minus in the coil 2, and minus in the coil 3. So this 3 added is going to be minus 35. From 60 to 90 degrees, from 60 to 90 degrees, we know that we have minus in coil 1, plus in coil 2, and minus in coil 3. So in total, it's gonna be minus 12.5 until 90 degrees. Now from 90 degrees to 120, we have 90 degrees to 120, we have plus, plus, and minus. So we have that this goes up to 12.5. Okay, now from 120 degrees to 120, let me see here, 120 to 240, 40 degrees. So here, let's say 240 is over here. What I mean, 120, 180, 240. We are gonna have, let me see, 120. We're gonna have plus, plus, and plus, so all of them add up. And we have our positive, 122, 240. And we know that the cycle is gonna repeat itself. So 240 to 270, we are gonna have, I can get already guess that it's gonna be 12.5, or we can look it up. So we have 140 to 270, we have plus, minus, plus. So we have 12.5. And you can do the rest of the math, but we know that it is gonna repeat itself. 300, and then it's gonna be minus 3. So this is the total MMF when we have the three coils.